Hello, this is Christian. My group project partners are Molly, Michael, and Tessa. We are Total Borons and we will be discussing chemistry. I will begin with chapters 1, 2, 3, and 4. Chapter 1 is titled Keys to the Study of Chemistry. There are 3 states of matter that are vital to chemistry and how things work. Energy will also be discussed. Matter occurs in 3 forms called states: solid, liquid, and gas. A solid has a fixed shape that does not conform to a container shape. A liquid has a varying shape that does conform to a container shape. A gas also has a varying shape and conforms to the container shape. Gases, liquids, and solids are all made up of microscopic particles, but the behaviors of these particles differ in the 3 phases. Particles in a gas are well separated with no regular arrangement. Liquids are close together with no regular arrangement. Solids are tightly packed, usually in a regular pattern. Here is a table that summarizes the properties of these 3 states. The next section of Chapter 1 involves energy. Energy is defined as the ability to do work. Work basically involves moving something. The total energy an object possesses is the sum of its potential energy and its kinetic energy. Potential energy is the energy due to the position of the object relative to other objects. Kinetic energy is the energy due to the motion of the object. Here are 2 examples of energy being expended. Chapter 2 is titled The Components of Matter. This chapter discusses Dalton's atomic theory and the formation of ionic compounds. John Dalton created his atomic theory of matter in 1808. He presented this theory in 4 postulates. All matter consists of atoms, tiny indivisible units of an element that cannot be created or destroyed. Atoms of a given element are alike. Compounds are formed when different atoms combine in fixed proportions. A chemical reaction involves the rearrangement of atoms. Dalton's atomic theory explained the mass laws by proposing that all matter consists of indivisible, unchangeable atoms of fixed unique mass. The next section will be about ionic compounds. Ionic compounds form when a metal transfers electrons to a nonmetal and the resulting positive and negative ions attract each other to form a 3D array. In many cases, metal atoms lose and nonmetal atoms gain enough electrons to attain the number of electrons as in atoms of the nearest noble gas. Each metal atom loses 1 or more electrons and becomes a cation, a positively charged ion. Each nonmetal atom gains 1 or more of the electrons lost by the metal atom and becomes an anion, a negatively charged ion. Here are some examples of ionic compounds. Magnesium loses 2 electrons and each chlorine gains 1 electron. Each sodium loses 1 electron and the oxygen gains 2 electrons. Each aluminum loses 2 electrons for 6 total, and each sulfur gains 2 electrons for 6 total. Chapter 3 involves the relationships of different formulas and equations and steps to writing and balancing a chemical equation. The formula is defined as the smallest possible whole number ratio of subscripts of the element in the formula. Because we are trying to find the smallest whole number ratio, we try to divide each subscript by an equal number to get the smallest number. We use acetic acid in this example. Each subscript is divisible by 2, so we divide by 2. This gives us the empirical formula, CH2O. The molecular formula is the formula of a compound in which the subscripts give the actual number of each element in the formula. Again, we use CH2O to get these answers. The structural formula then provides a visual of how the atoms are placed and connected within the compound. The structural formula for CH2O is given. Writing and balancing a chemical equation was also an important topic in Chapter 3. The first step is to translate whatever the statement is into a skeleton equation. To make an equation, one places the reactants on the left of the arrow and products on the right, with blanks in front of each formula to account for each atom. The next step is to count the atoms of each element in both the reactants and products. Coefficients are then placed in the blanks to finally balance the equation. Here's an example. Chapter 4 involves the 3 classes of chemical reactions. We will first start with the acid-base reaction. These occur when an acid and base are placed together. They react, neutralizing the acidic and basic properties, producing a salt. An acid is a substance that produces H plus ions when dissolved in water. A base is a substance that produces OH ions when dissolved in water. Next type of chemical reactions are called precipitation reactions. They can be written as molecular, total ionic, or net ionic equations. The molecular equation shows species reacting as their molecular formula with all natures included. The total ionic equation shows species reacting with their ionic components, and only aqueous is needed. The net ionic equation has the spectator ions removed. Here's an example. Finally, we will discuss oxidation, redox reactions. These are defined in the book as the net movement of electrons from one reactant to another. Oxidation numbers are assigned to identify a redox reaction. Oxidation is the loss of electrons and is shown by an increase in oxidation number. Reduction is the gain of electrons and has a decrease in oxidation number. The oxidizing agent is doing the oxidizing, while the reducing agent is doing the reducing, and they occur simultaneously.
Borons, and today we will be covering chapters 5 through 8. The first chapter we will be discussing is chapter 5, Gases and the Kinetic Molecular Theory. Section 5.1, Overview of States of Matter. There are three states of matter: solids, which have a fixed shape regardless of their container due to their particles being held together closely and rigidly; liquids, which adopt their shape to their container and have particles that are close to each other but can still move around; and gases, which adopt to their container shape and fill it due to their particles being far apart and moving randomly. For this chapter, we will be focusing on gases and their properties. Gases vary from other states in several ways. The volume of a gas changes significantly with the pressure and with temperature, meaning that when the pressure exerted on the gas increases, the volume of the gas decreases, and when the temperature of a gas increases, the volume increases, and vice versa. Gases also flow freely. This means that the particles of the gas are able to move around more freely than those of solids or liquids. Gases have relatively low densities, meaning that solids and liquids are more dense, about 1,000 times more dense than gases. Gases also form solutions in any proportions. Gases are able to mix. While if two liquids are mixed, not all will form solutions, and solids are unable to form solutions. The picture on the left shows the three different states of matter. The picture on the right shows different equations used to determine properties of a gas, including volume, pressure, temperature, and amount of gas present in a given sample. These are the gas laws. Section 5.2, Gas pressure and its measurements. Gas particles move randomly within their containers, often colliding with the walls of the container. The force of this is the pressure of the gas. Pressure is defined as the force exerted divided by the surface area. Gas pressures can be measured using a barometer or a manometer. Barometers measure pressure based on the height of a mercury column, while manometers, open-ended or closed-ended, measure the pressure of a sample of gas. Examples of both are shown in the pictures on the right. Pressure is measured using different units. These include the Pascal, atmosphere, millimeters of mercury and its equivalent, the torr, and pounds per square inch. These are listed in the table to the right. We will now be covering Chapter 6, Thermochemistry, Energy Flow and Chemical Change. Section 6.2, Enthalpy, Changes at Constant Pressure. Enthalpy is a thermodynamic variable that relates directly to the energy changes at a constant pressure. The enthalpy of a system is the initial energy plus the product of pressure and volume. The following equation defines the change in enthalpy. The change in enthalpy is equal to the change in energy plus the product of pressure and change in volume. The change in enthalpy is equal to the heat absorbed or released at a constant pressure. Knowing the change in enthalpy can help us determine information about the change in energy as well. Enthalpy can be defined as either exothermic, releasing heat and decrease in enthalpy, or endothermic, absorbing heat and increase in enthalpy. Section 6.4, Stoichiometry of Thermochemical Equations. A thermochemical equation is a balanced equation that includes the enthalpy change of the reaction. The enthalpy change has two aspects, sign and magnitude. Two things that are needed to understand thermochemical equations are balancing coefficients and thermochemical equivalence. Balancing coefficients can include fractions to specify the magnitude of change in enthalpy for a set amount. Thermochemical equivalence is this idea that a certain amount of substance is thermodynamically equivalent to a specified quantity of energy. These act as a conversion factor that can be used to find the amount of heat transferred when a substance reacts. The below figure shows the relationship of amount of substance and energy during a reaction. Now we move on to Chapter 7, Quantum Theory and Atomic Structure. Section 7.1, The Nature of Light. Light acts as both a wave and as particles. The wave nature of light can be described by their frequency, wavelength, and amplitude. These characteristics fall under different classifications on the electromagnetic spectrum. The electromagnetic spectrum includes light in the form of gamma rays, X-rays, ultraviolet, visible light, infrared, and radio waves. Light also behaves in different ways according to what it interacts with. It can experience refraction and diffraction, which indicates that the energy from the light is wavelight. Light can also behave as a particle. The particle is described as a photon, a tiny packet of energy. Each energy packet is called a quanta, which is also the smallest quantity of energy that can be emitted or absorbed. Planck's constant, quantum numbers, and the speed of light are all characteristics that help better describe the energy and properties of light. The diagram on the left is of the electromagnetic spectrum. The photo in the middle shows an example of amplitude and wavelength. The photo on the right shows examples of wavelength and frequency. Section 7.4, Quantum Numbers and Energy Levels. Quantum numbers are numbers that are used to specify a property of an orbital or an electron. There are three main quantum numbers that we will focus on. The principal quantum number, n, which describes the size and relative distance from the nucleus an orbital is. This is the energy level. The angular momentum quantum number, L, describes the shape of the orbital. The magnetic quantum number, m sub L, describes the orientation of the sublevel. The levels of the atom are further divided into sublevels. The sublevels of the orbital are given values 0 through 3, each corresponding with a different sublevel such as S, P, D, and F. The orbital is made up of a combination of the different quantum numbers, and each electron within the orbital has a unique set of quantum numbers according to Pauli's exclusion principle. The table to the right shows the different combinations for quantum numbers. Chapter 8, Electron Configuration and Chemical Periodicity. Section 8.2, General Principles of Electron Configuration. Outer electron configurations tend to be similar within a group on the periodic table. Within the main group elements, which includes the S block and the P block, the outer configurations are identical. Each outer shell has the same number of electrons present. However, the transition metals tend to have variations. The way the orbitals fill up is by increasing energy. The levels and sublevels of the element are filled in order of increasing energy, following the sequence of elements across the periodic table. The S sublevel will fill up before the P sublevel, and so forth. The electrons that fill up the orbitals can be categorized three different ways: inner or core electrons, outer electrons, and valence electrons. The group and period numbers also help describe the electrons in an element. The period number is the n value of the highest orbital, and the atomic number is the number of electrons present. Section 8.4, Trends in 3 Atomic Properties. The 3 atomic properties are atomic size, ionization energy, and electron affinity. Atomic size is defined as a measure of how closely one atom lies next to another. Atomic size is determined from the distances between nuclei of adjacent atoms. This characteristic increases as you move to the left and down the periodic table. Ionization energy is the amount of energy that is needed in order to completely remove 1 mole of electrons from 1 mole of gaseous atoms or ions. The energy must be strong enough to overcome the attraction between electrons and the nucleus. Ionization energy increases as you move to the right and up the periodic table. Electron affinity is described as the energy change in kilojoules accompanying the addition of 1 mole of electrons to 1 mole of gaseous atoms or ions. This increases as you move up and to the left on the periodic table. Both diagrams show the different trends in the 3 atomic properties.
Pictured here is a covalent bond, which is a chemical bond in which atoms are bonded together through the sharing of electrons. In a pair of covalently bonded atoms, the electron density is highest here between the 2 nuclei. These shared electrons then count as valence electrons for both atoms simultaneously, such that the outer layer of each electron is full, and each atom has a neutral charge. The pairs of electrons that are not involved in bonding are called lone pairs. Now, since this is a hydrogen molecule, there are no lone pairs, so both these electrons count as 2 electrons for each atom, filling the 1s orbital. The 3 properties that we examine in covalent bonds are bond order, bond energy, and bond length. Bond order is the number of bonds between 2 atoms. As you can see here, the bond order is 1 because there's 1 shared pair of electrons. Bond energy is the energy required to break the bond in 1 mole of gaseous molecules. The bond length is the distance between 2 bonded nuclei. So that would be this distance between the 2 nuclei. The electron C model is a qualitative description of metallic bonding, proposing that metal atoms pool their valence electrons into a delocalized sea of electrons in which the metal ions are submerged in an orderly array. As you can see here, here's the various nuclei of a given metal, and in the shaded area is where electrons can exist. And the electrons move freely throughout the shaded area. In metallic bonding, there are no anions. Metal ions are not held together as rigidly as in ionic bonding. There are no shared pairs of electrons, and 2 or more metals form allies, which are solid mixtures of metal of varying composition. The electron C model shows that valence electrons of the metal atoms in a sample are highly delocalized and attract all the metal cations holding them together. The electron C model pictured here helps explain why metals are conductive, malleable, and ductile. The electrons are free to move around, making metals conductive. The atoms are not rigidly fixed in place but can also move around each other, which allows metals to bend and not break. A Lewis structure is a structural formula consisting of electron dot symbols with lines as bonding pairs and dots as lone pairs. The octet rule applies where each atom in a molecule fills its outer layer with 8 electrons, 2 for hydrogen. So as you can see here with methane, you have carbon. Each line represents a shared pair of electrons, so that would be like 2 valence electrons for each line for carbon, and 2 for hydrogen. So therefore hydrogen has a full valence shell of 2, since hydrogen is the only one that has a valence shell that maxes out at 2, and carbon has its full shell at 8 valence electrons. For compounds with the general molecular formula AB sub N, place the atom with a lower group number in the center because it needs more electrons to attain an octet. Usually, this is also the atom with a lower electronegativity. If the atoms have the same group number, place the atom with the higher period in the center. And as you can see, that is the case with NO3-. Pictured is a Lewis structure. Notice that the atom with the lowest group number is in the center. The other atoms surround it. To draw a simple Lewis structure, begin by positioning the atoms appropriately. Make a note of the total number of electrons. So in NO3-, there's 24 total valence electrons. Connect the outer atoms to the central atom with single bonds, one line. Each line represents a shared pair of electrons. Use dots to represent the remaining electrons on the outer atoms so that they all have 8. Finally, place all remaining electron pairs on the central atom. Each atom should have 8 valence electrons, 2 for hydrogen. So as you can see here, oxygen here has 2, 4, 6, 8. This one has 2, 4, there's a double bond, so 6, 8. 2, 4, 6, 8. In nitrogen, you have a double bond and 2 single bonds, which a double bond is 2 and 2, so that's 4, and then you have 2 and 2, and that's 4 more, and that's 8. So the octet rule is followed with NO3- or nitrate. There are a few exceptions to the octet rule. The first occurs in molecules that have one odd electron. Some molecules have an unbonded electron, or free radical, that makes the molecule extremely reactive and paramagnetic. When two such molecules react, the lone electrons pair up, connecting the molecules. Another exception concerns molecules with electron-deficient atoms. Molecules based around boron, beryllium, or aluminum fit this description. Such molecules tend to react with other molecules so the central atom can obtain an octet. So as you can see here, there's boron with 3 fluorines. Now, in this case, the boron only has 6 valence electrons, and boron tends to have less than 8 valence electrons. The last exception concerns expanded valence shells. Sometimes the central atom expands its valence shell to hold more than 4 pairs. Expanded valence shells occur only in nonmetals from period 3 or higher because they have d orbitals available. Now, one such element that fits this criteria is sulfur. And as you can see here, in sulfur hexafluoride, or SF6, you have the S, and it's bonded to 6 fluorine atoms. So when you add up the pairs, the shared pairs, you have 2, 4, 6, 8, 10, 12. So sulfur has 12 valence electrons in this molecule. It just so happens that the highest number of electrons to be found in expanded valence situations is 12, as in sulfur hexafluoride, which has 6 bonding pairs.
This is Chapter 11, and we will be discussing types of hybrid orbitals and the central theme of molecular orbital theory. Hybrid orbitals are also known as hybridization. There are many different hybridizations, but we'll just go over 3. sp hybridization is the s orbital and one of the p orbitals from the carbon's second energy level are combined together to make 2 hybrid orbitals. Because this type of sp hybridization only uses one of the p orbitals, there's still 2 p's left which the carbon can use. Those p orbitals are at right angles to one another and the line formed by the hybrid orbitals. Here's an example of CO2. There's 180 degrees and this is linear. sp2 hybridization uses the s orbital and 2 of the p orbitals from the second energy level of the carbon to form 3 hybrid orbitals. Because of this type of sp hybridization only uses one of the p orbitals, there are still 2 p orbitals left which the carbon can use. Here's an example of sp2, which is SO3, and you can see the 120 degree angle right there. This is triangular planar. sp3 hybridization results from the combination of the s orbital and all 3 p orbitals in the second energy level of carbon. Because this type of sp hybridization only uses one of the p orbitals, there are still 2 p orbitals left which the carbon can use. Here's an example of sp3, and this is CH4, and you can see right here a 109.5 degree angle, and this is tetrahedral. Next, we'll discuss the central theme of molecular orbital theory. In chemistry, molecular orbital theory, also known as MO theory, is a method for determining the molecular structure in which these electrons are not assigned to a specific individual bond between atoms, but are treated as moving under the influence of the nuclei in the whole molecule. The properties of electron within the atoms are fixed by quantum mechanics to form orbitals that contain these electrons. The property of electrons within the atoms are fixed by the quantum mechanics to form orbitals that contain these electrons. While atomic orbitals also contain electrons assigned to a single atom, molecular orbitals, which surround a number of atoms in the molecule, contain valence electrons between the atoms. The MO theory provides a large perspective on chemical bonding. Here you can see the structure for molecular bonding, and the first one is without 2s and 2p bonding. You can see the structure of that compared to with the 2s and 2p bonding. You can see a difference in shape right here compared to this bottom one.